Hi, welcome to Elastic Load Balancing Net 402, a year of innovation. I'm John Zobrist, Assist Dev Manager on the ELB Customer Success Team. Today we're going to talk about the different things we've launched over the last year for Elastic Load Balancing. We'll get into a few topics more deeply, GRPC on ALB and HTTP2 to the backend, our new HTTP Desync Mitigation mode, which helps mitigate attacks on both Classic and Application Load Balancer, and then our new Gateway Load Balancer, which lets you put in firewalls and different security devices directly into the route tables of your VPCs. So over the last year, we had quite a few interesting launches. UDP support for NLB lets you send UDP traffic to your targets. And we added IP targets, which enables you to use things like AWS Fargate or to route those connections and requests outside of your VPC to your Direct Connect or VPN connected endpoints. We added ALPN on NLB for TLS listeners. And so when you're offloading your TLS to the network load balancer, this lets you use ALPN so you can start your connections directly H2 on the front end. And then we added weighted target groups for application load balancer. This lets you have things like blue-green deployments or A/B testing or different things where you want to send some traffic for a set of rules to one group of targets and a set of rules or the same set of rules but send a percentage of traffic to the other targets. And we also support stickiness there, so we do try to keep things to the same target, and we can enforce that with stickiness if you want. Then the EKS and Kubernetes teams launched a new ingress controller for application load balancer. And this lets you really control your application load balancer and set multiple applications in your cluster exposed from the same load balancer. What we had heard a lot was customers wanted to have more flexibility in controlling and configuring a single ALB as opposed to creating an ALB for every single service they were trying to expose. Then we launched IPv6 on network load balancer. So this lets you get those mobile networks or IPv6 or future connectivity, a lot of cable providers. Lets you bring IPv6 all the way to the front door of your network load balancer. We do still do IPv4 to the back-end targets right now on that, but we do support the full IPv6 on your external load balancer. And we'll give you a dual stack name when you do that, so you can use dual stack and you'll get the quad A IPv6 address. This will help you migrate or plan for future connectivity as IPv4 addresses continue to be exhausted. Then we added ALB support on Outposts. So if you don't know about Outposts, they're the AWS in your data center where you can bring an Outpost rack and put it directly in your data center and run all the applications you can run on AWS, or a lot of the applications you can run on AWS directly in your data center. If you need something like low latency or you already have a data center footprint, the ALB lets you load balance those resources now running directly on your Outpost. Then we brought WAF fail open for ALB. A lot of customers who use WAF really want every request to either go through WAF or not arrive. And what this does is lets customers who want to be able to say, you know, I don't always want to fail those requests. Sometimes I want those requests to complete, but I want to know about it. And so WAF fail open lets you enable that on your ALB where you're using WAF. When it does fail open, you will get a notification in your access log that says it failed open. And that happens if we have a trouble connecting over services to WAF. It's useful if you want to come back and audit the security, but you're not really expecting that to be an attack, or you have other mitigations in place, and you want the requests to go through. So again, we're going to dive a little deeper into HTTP2 and GRPC to our targets on ALB, the Desync Mitigation mode, the Gateway Load Balancer. And let's get started with GRPC to targets. So we launched GRPC support on Application Load Balancer this year. And with that, we brought HTTP2 to the target groups. The gRPC protocol is a Google protocol used in microservices. It's useful if you want to have a lot of things connecting in different ways through your load balancer and sending non-HTTP data. gRPC is a first-class protocol for ELB, so we fully support it on ALB. We support all the different kinds of calls, the streaming client server, the bidirectional streaming, or just unary calls like a normal HTTP request. And then we also bring HTTP2 to your target group. So we had a lot of customers who said, I'm doing things with H2 that I like, and ALB gives me that on the front end, easy termination of H2, but I don't really have a mechanism to bring that to the target group, and I want to do something specific with H2. This enables that. And specifically, we heard gRPC is what people want, so we made that a fully fledged, fully supported protocol of its own. And let's look a little bit how that looks. So you're going to configure your gRPC protocol on your target group. Right now, previous to this, we didn't really have a concept for target group protocol, and we added one here. And so default previous target groups are HTTP1. There's also Lambda target groups, but we won't really get into those because you're not routing requests to Lambda this way. So H1 was the default. All your existing target groups that are receiving HTTP requests are all getting those over HTTP 1.1. With gRPC and HTTP2, you could now create those target groups to be either gRPC or HTTP2, and then the requests from the load balancer can be routed directly to them over those protocols to the back end. This does introduce some compatibility issues because you can't do some things like upgrade an HTTP 1.1 request to an H2 or gRPC request, but you can downgrade. So let's look quickly at what these, what each protocol coming in the front door looks like going to the different target groups. So right now, if your clients are talking HTTP 1.1, it's going to work to your HTTP 1.1 target group. It's going to work to your HTTP. It's not going to work to your HTTP 2 target group or your gRPC target group. And the reason for that is we don't have a clean way to upgrade those protocols, and there's a lot of things in them that really don't translate from HTTP 2 or from HTTP 1 to HTTP 2 or gRPC. Then we go to HTTP 2, and that's going to work to HTTP 1.1 just like it does now. We receive the requests over H2 and we convert them into HTTP 1.1. That's what we've been doing since the launch of ALB, since we supported HTTP 2. That'll also though work to HTTP 2 target groups. Of course, you're sending HTTP 2 on the front end. You're going to get the same thing on the back end. We are still routing the individual HTTP requests. And then if you send it to gRPC, you will get that working also, but it's going to be with limited functionality, and your gRPC target group has to support the HTTP 2 post or the HTTP 2 request that actually comes to it. And that's because we're using HTTP 2, which enables gRPC really. So let's look now if you have a gRPC target group, the requests to gRPC requests. The requests to HTTP1 aren't going to work because we can't translate gRPC into HTTP1. They're going to work for HTTP2 as long as your HTTP2 target group supports what the client is requesting. And of course, they'll work to gRPC target groups. And again, the HTTP2 target has to actually support the gRPC protocol. So when you create a target group and you now have this option to select the protocol version, the health checks are going to also have the HTTP2 or gRPC version. And with HTTP2, it's similar to an HTTP1 health check, but we'll actually send them as HTTP2 requests. With gRPC, it's a little bit different. You can specify the protocol version that needs to come back from the client, from the target for it to be considered healthy. And then again, HTTP2 target groups support gRPC only one way, and as long as that the backend supports those gRPC requests. So we're not going to enable gRPC to non-gRPC targets. And here's a summary table. Configuring this is just like configuring any other target group. You just have some new options now where you get to specify the protocol version. And this is where you're creating it. It's a target level attribute. The health checks are going to be going to the target group. When you have, right now, this is what you've got for HTTP 1.1 health checks. You've got the different options. You can specify the timeouts, what port to use, and then what success codes. For HTTP 2 or for gRPC, this is where you can specify a gRPC response code. And the default will be 12 there, which is unimplemented, but you can pick whichever gRPC response code you want your health check application to return. So let's dig into the routing of these requests. So of course, they're all going to come into the load balancer over your different listeners. We do support all the different methods for gRPC communication. And let's just kind of dive into what those look like. So a unary call, we're going to have, it looks like a single HTTP request. In this case, we do /health for an example, like a health check. It could be, other information that the client is requesting. The client's going to send one request. The target's going to send one response back. Then we're going to have a client-side streaming workload. Now this could be something like I'm streaming my information about my application, performance information, or logs, and they're going to the target group that is gRPC. We're going to send multiple requests from the client and then ultimately get one response back. And then server-side streaming is just the opposite. So this could be something like a video streaming workload or a data streaming workload or ingestion to a client to do some processing. And we're going to send a single request from the client, and then we're going to see multiple responses coming back over gRPC. And then, of course, we support bidirectional streaming. This is where you can have something like chat or something like your agents talking back and forth to your applications, and you'll see many client requests, many client responses. It's a lot of two-way chatter support for client and server streaming. So at high level, gRPC is a protocol that helps you do remote procedure call, RPC communication. AOB supports it as a first-class protocol. This lets you do all kinds of communications for your microservices or other clients, and we support all the different methods and health checks for gRPC. So let's talk about desync mitigation mode. So over the last year or so, there's been a lot of talk in the security world about desynchronization of HTTP requests. And we're going to cover what that means, and then what HTTP proxies can do, what ELB can do, and what our new desync mitigation mode can do. We'll also cover the configuration options there. But first, let's talk a little bit about why we have desynchronization, or why it's a possibility. And in this case, let's just talk generic reverse HTTP proxy, which an application load balancer is a layer 7 reverse proxy, primarily for HTTP, but also gRPC now. So when we do proxying like this, we're actually using TCP connections from clients to receive HTTP requests, and then we're using TCP connections to targets to send those requests over. We're sharing these connections between clients to the targets. So we'll have the case where one TCP connection to a target can have many requests from different clients. The way we do this is, since HTTP is ordered, we send it in the same order we receive it, and we can only send one request at a time. So this is kind of what lays the groundwork for the potential for desynchronization. This is because of HTTP 1.1 supports connection keep alive. And this is a setting that's default on HTTP 1.1, and something that if you don't set connection close is always happening. It does give us a lot of performance improvements if you're running a really performant workload. HTTP connection keep alive is a lifesaver for your backends not having to churn through those connections, and really helps your whole workload through your ELB scale. So a normal HTTP communication is sequential. So a client's going to send one request, backend's going to send one response, the HTTP proxy is going to route those through to each other. There are cases where you can send HTTP pipelining, which the ALB supports on the front end. So your clients can send multiple requests, but will always respond with those in order. So if you have multiple backends responding to different requests, we will send those back to the client in the same sequence that we received them. Because of this, the boundaries of those requests is very critical for determining where a request ends, where it sends, where to start the next request. And desynchronization is what really exploits that, a difference in where we determine the end of a request or the end of a connection. And again, this is something that HTTP proxies inherently, if the HTTP proxy has a different interpretation of mixed headers or different variations of headers than the backend HTTP server, you might end up with something where you've got a different boundary on an HTTP request. And when an attacker or somebody comes along and wants to exploit that, they can intentionally inject those different kinds of mismatches between the boundaries. And when that happens, the net effect is that they prepend data to the next request. So here in this example, we've got a client sending in different sequential requests. An attacker comes in and sends a request with a mixed message that confuses the load balancer and backend server's synchronization state, or it makes them interpret it differently, and that causes part of the attacker's request to be sent back to the first client. So a few things about our classification system. So when we see a request now, and our library that we built for this, we did open source. You can go look at it on GitHub. You can incorporate it into your own HTTP proxies, and you can see all the different tests we have and investigate, how the nuance of each of these specifications. So compliant, we're going to have requests that are just 100% RFC 7230 compliant. There's no known security risks. It's nothing. We don't do anything except route those requests. Those are the good requests. Acceptable really are good requests also, but they may not be fully RFC 7230 compliant. There's no known security issues, and they're not really doing anything with the specific headers related around desync mitigation. But we will allow those in general. And the desync mitigation mode is deployed on all load balancers globally for ALB and CLB. All of our HTTP listeners get this, and the default mode will be defensive, which we'll get to a little bit in the future. In defensive, though, we're going to let acceptable requests through unaltered. Then we've got ambiguous requests, and this is where we see something that we know might cause a desync, but it's not a known exploit. It's not something where we say this is 100% an attack that we've seen in the wild, but it's ambiguous. And in defensive mode, which is our default, we're going to go ahead and we're going to still do a mitigation there where we block the connection from serving multiple requests. And we'll get into exactly what that looks like in just a second. And then we have severe, and this is where we see something that is literally, we know this is an attack, we know this is a fingerprint of something we've seen before that can directly lead to exploit and is likely malicious. Those will reject with the 400 response directly to the client in defensive mode. So let's look at what that looks like. When we've got our attacker sending requests, we're protecting against ambiguous requests by setting connection close on both sides of the connection. So if an attacker sends in a request that's ambiguous and we send that to a backend, we will close both of those connections after the first part of that request. So wherever the backend sees that request as terminating, it's going to respond to that. And we won't let any more data use that TCP connection again. So we'll set connection close, and then we'll close with a TCP fin both sides of those connections. So the net effect of that is we're going to have the request from the client might have used the same TCP connection that the request from the attacker used, but as soon as we saw that ambiguous request, we shut that connection down. And now the client request has to go over another connection. No request will be sent to that same connection. We've blocked whatever's left there on the request from coming back to any clients. And that is, of course, our default mode, defensive. In default mode, we reject severe attacks with an HTTP 400. So in this case, we don't even let the request in to the load balancer. We're returning a 400 to the attacker. The client requests are never affected or changed, and we'll emit a 400 error metric for that. So we protect against acceptable and severe requests and ambiguous requests in strictest mode by rejecting all of those with 400. So even if it's an acceptable request, if you enable strictest mode, what you're telling us is, I don't want anything that isn't 100% RFC compliant. And again, the open source part of this, you can go look at what each of these categorizations in our testing does and see kind of where we're drawing these lines, and of course use that library in your own code to implement similar kinds of defenses. But again, in strictest mode, we reject all those with 400, so those requests aren't ever coming in, even though we're not doing the connection close because we just don't accept the requests. We do have a new metric for this, so you can monitor this in your CloudWatch dashboards or configure alarms. Non-compliant request count. This is something that lets you see the grouping of all of those requests that aren't going to be in the first bucket of completely safe RFC, 100% compliant. And this is something that's useful if you're troubleshooting or if you're, want to monitor your workload and see if you can enable strictest mode. This is the first place to look. Go see this, and if you see something here that this is completely clean, you can probably safely enable strictest mode. Your clients aren't really using these kinds of things, or the headers that look suspicious or are malicious. So we have access logs for this also, and the two new fields we added to your existing ALB access logs are the classification and the classification reason. So I recommend you go look in the docs for the access log information because it's pretty detailed. In the classification, we're going to tell you that ambiguous, severe or acceptable, and then we're also going to tell you the reason for that. And the reasons we have for this is a big long list. So I don't expect you to read this slide because it's a big list. But see the docs. Go look at the docs and see what each of these are, why we request them, or which log line is going to map to which reason, and then tell you what we classify that as. And you can use this to determine if your application can safely be run, in severe mode, or if you have any impact from running in severe mode, and you need to change things, maybe on the client or the upstream from the load balancer to help not have those kinds of requests. So in summary, we're accepting all the requests that we think are safe. The ones that we get into the gray area in the default defensive mode, we're going to block those future requests from using that connection. We're going to block desync by not allowing reuse of that connection. And of course, we're blocking severe. Now, we did launch monitor mode. If you have a legacy application where maybe you're doing something that you have a reason for having the connection stay open in ambiguous mode, or you have requests that look severe to us, then monitor mode is something that you can use there to see what or to allow the traffic while you work on upgrading or fixing whatever could be causing that. And in general, if you're seeing something where you've got severe, that's not something where you probably want to enable monitor mode. But if you want to do that for troubleshooting or for a migration period, we do have that option. So in summary, this is on all our load balancers, application and classic. We did bring this to classic load balancer, even though it's our legacy load balancer, because we think security is the #1 priority, and we absolutely thought this was a security risk, and we needed to help protect our customers. It is defensive mode by default. We think that gives you the best trade-off of protection with minimal impact to your actual workload. And then, of course, you can configure that to change if you want to be more strict or less strict. And we've got metrics and access logs to inform you about what the different requests you received were and why they were classified that way. Okay, so let's talk about Gateway Load Balancer. This is our new load balancer that we just launched this year. This is something that we're really excited to bring to everybody. We've had a lot of customers over the year who have worked with us for different challenges they've run into trying to accomplish exactly this. And what this lets you do is reduce the complexity and deployment of your security devices into your network. So currently we have a lot of customers who are building things that would route through a load balancer on one end to some host and through another load balancer, or they'd use static IPs of their firewall devices. And we wanted to help enable all of the good things about AWS, like elastically scaling your security devices, having deep integration with the network so you can do this as a route. And then we also partnered with a lot of vendors. There's a marketplace for this. You can go out there and get most of the vendors that you're used to using in your on-prem have an option to integrate with Gateway Load Balancer. So let's dive into that. Gateway Load Balancer, one of the nicest things about it that people really love is the transparent network traffic. So you're going to be able to just intercept traffic, layer 3, send it to your networked appliance, do whatever you want there, whether it's auditing or security or rejecting the connection, and then it routes back out. You don't have to worry about IP addresses. IPs don't change. We're using private link endpoints and hyperplane integration to make this work transparently for you. And then you can bring all of the different security or intrusion detection or different use cases you have for auditing or other compliancing. And again, the reason we did this, we have so many customers who have different compliance requirements or their security teams had specific asks. This really enables you to put this directly into your VPC as a first-class citizen with all the AWS best practices around scaling and availability. So before we had Gateway Load Balancer, and we have a lot of customers still doing this today because Gateway Load Balancer is still very new, you had something where you had a source and you had a destination and you might have an active-passive failover between them, and you had to really route the connections, not necessarily by routing, or you had to manage that all yourself. And then there were challenges with scaling that made it harder for you to change those routes dynamically or update things so that your network traffic transparently goes through the appropriately scaled devices. Gateway Load Balancer, we made that easy. You just have an Appliance Fleet. They support the Genevieve protocol that we use for Gateway Load Balancer to route layer 3 traffic to them. We support all the built-in scaling. You can register auto scaling directly to it. You can have, we're doing load balancing there. It's fault tolerant. And the most important thing, it's transparent to the network traffic. So if we look at implementation here, so what are the different components of the Gateway Load Balancer? We're going to have the Gateway Load Balancer itself, which is going to use that VPC endpoint, which you can insert into your routing table and it acts as a next hop. So you can have a source and a destination, and as the administrator or the owner of the VPC, you can go in there and configure this traffic to go directly through your Gateway Load Balancer. Then your Gateway Load Balancer is going to send the traffic to the Appliance Fleet. We're doing health checks there. We do auto scaling. We do all the things that are best practice and ELB really enables. And we're transparently integrated with EC2's network to make sure all of that works quickly and transparently. And we do that with AWS Hyperplane. The big benefits here, you get the scaling, you get the fault tolerance. Just like having an ELB, you don't have to worry about IP changes. You don't have to worry about updating when things scale, when traffic grows. It's just all handled transparently. And you can use this for some different implementations to have different security domains, admin domains, or share across AWS accounts. Since we're using private link, it doesn't really matter. The VPC endpoint just needs to be in the same availability zone in the same region as your gateway load balancer. So just like exposing your service through a VPC endpoint and an NLB, you can expose into any VPC. And let's take a look at a couple of those in just a second. And you can use Appliance Fleets here to scale everything. And you send traffic by just updating your routing tables. Our launch partners. So we had many launch partners. We heard customers asking for these exact services. All the big firewalls, security devices, things that they're already using in their on-prem. Now they can run those things transparently on the gateway load balancer in AWS. Tap into existing VPCs, have centralized management and control of those, and then get all the benefits of normal elastic load balancers. So one use case here is easy. It's easy to expose your appliance or security VPC. You can now centralize that, and you can have your security team or your compliance team owning their own VPC and then tapping into all these different VPCs in the same region with a gateway load balancer. And that lets you have a single place where all these different connections can go. We're managing all the flows bidirectionally to make sure that they go to the right places. We're doing all the security between the different components to make sure that everything is delivered directly to your backend securely. And then your backends behind your gateway load balancer can be your firewall fleet or your compliance fleet. And we'll manage connections and resources and routing between them. Again, auto scaling and all the great stuff there. And you can also do this if you've got more VPCs and you just want to route between instances, or put your transit gateway in there and just tap directly into your transit gateway routing table. You can do this for north-south traffic inspection or east-west traffic inspection, or both at the same time with multiple gateway load balancers in the same VPC and in the same hops. And this lets you, again, the north-south, east-west inspection. You can do this with the same fleet. You can do this for the same VPCs or for different VPCs. And then you can also do NAT inside or outside of your appliance fleet VPC, depending on how you want to manage the routing. We try to make that as flexible as possible. So that's it for my session today. Thank you all for coming. Check out the related session, Net 301, Choosing the Right Load Balancer for Serverless Applications. And you can learn more about all the different things that Elastic Load Balancers give you with the different AWS serverless ecosystems. So thanks again, and be sure to check out the survey.